Tonight, we're going to talk about Saturn, the sixth planet from our Sun, nearly 900 million miles away, with those magnificent rings that have captured human imagination for over 400 years. A destination that seems peaceful and majestic through our telescopes, but where distance, radiation, and the brutal mathematics of rocket propulsion create obstacles unlike anywhere else in our solar system. And by the end of tonight, you're going to understand why anyone who travels there will face challenges so severe, so fundamentally unforgiving, that they might never make it back home. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Saturn looks peaceful through a telescope. Beautiful, almost serene, with those elegant rings circling its pale gold body. It's the second largest planet in our solar system, massive enough to fit 764 Earths inside its volume. When you see images of Saturn, when you see those stunning photographs from Cassini showing the intricate structure of the rings, the hexagonal storm at the North Pole, the small moons embedded in the ring gaps, it looks like somewhere you might want to visit, a destination, a place to explore, a world waiting to reveal its secrets. But that impression is dangerously misleading. Saturn is one of the most hostile environments in the solar system. Not in obvious ways like the crushing surface pressure of Venus or the radiation-blasted hellscape near Jupiter's moon Io. Saturn's dangers are more subtle, more insidious, and in many ways more absolute. The challenges don't announce themselves. They accumulate, layer upon layer of difficulty that builds into an almost insurmountable barrier to human exploration. Let's start with the basic challenge of getting there. Saturn orbits at an average distance of roughly 886 million miles from the Sun, or 1.43 billion kilometers. That's nearly 10 times farther from the Sun than Earth. To put this in perspective, if Earth's orbit were the size of a quarter, Saturn's orbit would be a circle nearly 8 feet across. The scale is difficult to grasp. At our planet's fastest spacecraft velocities, the journey takes years. Cassini, the most successful probe ever to orbit Saturn, launched in October 1997 and arrived in July 2004. Nearly 7 years in transit. 7 years of continuous travel through the void of space, and Cassini wasn't carrying humans. It didn't need radiation shielding, designed to protect living tissue. It didn't need any of the massive infrastructure required to keep people alive for 7 years in the hostile environment of deep space. For a crewed mission, you'd need a spacecraft many times larger, more massive, more complex, more expensive. Every additional kilogram of mass requires more fuel to accelerate away from Earth and more fuel to decelerate when you arrive at Saturn. The rocket equation, formulated by Konstantin Tsiolkovsky in 1897, is brutally unforgiving. The equation states that the change in velocity your spacecraft can achieve is proportional to the logarithm of the ratio of initial mass to final mass. What this means in practical terms is that as your payload mass increases, the fuel mass needed increases exponentially. It's not linear. Doubling your payload mass doesn't just double your fuel requirement. It more than doubles it, often significantly more, depending on your propulsion system and desired velocity change. This is why rocket design is so difficult. This is why we can't just build bigger rockets and solve all our problems. The mathematics work against you. Adding enough supplies and systems to keep humans alive for a 7-year journey makes the spacecraft so massive that launching it becomes extraordinarily difficult. You'd probably need multiple heavy lift launches, maybe 10 or 20 separate rocket flights, carrying components into orbit, where they'd be assembled piece by piece to form the complete spacecraft, building the ship in Earth orbit before departure. That's expensive, complicated, and risky. Every docking operation, every assembly sequence, every connection between modules is a potential failure point. The International Space Station took over 40 missions and more than a decade to assemble, and it's much smaller than what you'd need for a crewed Saturn mission. It doesn't have propulsion systems capable of interplanetary travel. It doesn't have the radiation shielding necessary for leaving Earth's protective magnetosphere. It doesn't have the fuel tanks, engines, or mission systems needed. Building a Saturn-capable spacecraft would be an even more massive undertaking. Then there's radiation, one of the most serious and least appreciated dangers of deep space travel. Earth's magnetic field, generated by the motion of liquid iron in our planet's outer core, creates a protective bubble called the magnetosphere that deflects most cosmic radiation and solar particle events. This magnetic shield extends tens of thousands of miles into space. It's the reason life could develop on Earth's surface. Without it, the surface would be bombarded with radiation that would make complex life impossible. Once you leave Earth's magnetosphere, you're exposed. Cosmic rays, which, despite their name, are not rays, but high-energy particles, mostly protons and atomic nuclei, slam through your spacecraft constantly. These particles come from exploding stars, from supermassive black holes in distant galaxies, from the violent death throes of stellar cores. They've been accelerated to nearly the speed of light by mechanisms we still don't fully understand. When they hit your spacecraft, they pass through the walls like they're barely there. Some hit atoms in the structure, creating cascades of secondary particles. Some pass completely through without interacting, and some slam into the cells of your body, damaging DNA, killing cells, creating mutations. Solar flares are another hazard. The sun periodically erupts, ejecting billions of tons of charged particles into space at speeds of several million miles per hour. These coronal mass ejections, as they're called, can deliver lethal radiation doses in hours if you're caught without adequate shielding. On Earth, we're protected. The magnetosphere deflects these particles toward the poles where they create the aurora, beautiful lights in the sky that signal deadly radiation being kept at bay. In deep space, there's no such protection. If a major solar flare erupts while you're en route to Saturn, you need to get into a shielded area immediately. This means your spacecraft needs a dedicated radiation shelter, a heavily shielded compartment where the crew can take refuge during solar particle events. This shelter needs enough supplies for several days because major events can last that long. It needs life support. It needs to be comfortable enough that people can survive in a confined space for extended periods. All of this adds mass. And mass, as we've discussed, is the enemy of rocket propulsion. Shielding helps, but perfect shielding is impossible. You can't block everything without making your spacecraft prohibitively heavy. The aluminum and composite materials used in typical spacecraft construction provide some protection, but they're not ideal. When high-energy particles slam into aluminum, they can create secondary radiation through a process called spallation. The incoming particle breaks aluminum atoms apart, creating showers of particles that can actually be more dangerous than the original radiation. Hydrogen-rich materials like water and polyethylene plastics are better. Hydrogen atoms are effective at absorbing and scattering radiation, because they're the right size to interact efficiently with incoming particles. Some mission concepts propose surrounding crew quarters with tanks of water, using the spacecraft's water supply as radiation shielding. This serves double duty, providing both shielding and the water needed for drinking, cooking, and hygiene. But even with optimal shielding materials, you can't shield perfectly. There's always some radiation getting through. And over a 7-year journey to Saturn, your crew will accumulate significant radiation exposure. This exposure is measured in sieverts, units that account for both the amount of radiation and its biological effectiveness. A typical chest X-ray delivers about 0.01 millisieverts. A CT scan might deliver 10 millisieverts. The average person on Earth receives about 2 to 3 millisieverts per year from natural background radiation, cosmic rays hitting the atmosphere, radioactive elements in soil and rocks, radon gas in some buildings. Astronauts on the International Space Station receive about 0.5 to 1 millisievert per day, roughly 80 to 150 millisieverts during a 6-month mission. This is well above normal Earth background, but still considered acceptable for space missions. The limit for NASA astronauts varies by age and sex, but is generally in the range of 1 to 4 sieverts over a career. These limits are set to keep the increased risk of cancer from radiation exposure below 3%. For a multi-year journey through deep space, radiation exposure would be much higher. Estimates for a Mars mission, which is much closer than Saturn, suggest crew members might receive between 0.3 and 1 sievert, or more, for the round trip, depending on solar activity and shielding effectiveness. A Saturn mission, being much longer, would likely result in exposures of 2 to 4 sieverts or even higher. This significantly increases cancer risk. It damages organs, potentially affects the brain and nervous system, and weakens the immune system. Radiation doesn't just increase cancer risk. High doses can cause acute radiation sickness. Lower chronic doses, the kind you'd receive on a long space journey, cause more subtle damage. They accelerate aging at the cellular level. They increase the risk of cataracts. They may cause cognitive changes, affecting memory and decision-making ability. Studies of atomic bomb survivors and radiation therapy patients show that even moderate doses of radiation have measurable health effects. By the time you arrive at Saturn, your crew is already compromised, already dealing with health effects from years of radiation exposure. And that's before we even consider microgravity. Microgravity, the condition of freefall that astronauts experience in orbit, is another serious problem for long-duration spaceflight. The term microgravity is slightly misleading. It doesn't mean there's no gravity. There's plenty of gravity in orbit. The International Space Station, orbiting roughly 250 miles above Earth's surface, experiences about 90% of the gravitational force that we feel on the ground. But the station and everything in it are in continuous free fall around Earth. They're falling, but moving forward fast enough that they keep missing the planet. This creates the sensation and effects of weightlessness. In the absence of gravity's constant pull on the body, human physiology changes dramatically. Bones lose density because they're not bearing weight and don't receive the mechanical stress signals that tell bone cells to maintain or build bone mass. The body, in its efficiency, decides that strong bones aren't necessary and begins breaking them down faster than it builds them up. Astronauts on the International Space Station lose about 1 to 2% of their bone mass per month, particularly in weight-bearing bones like the hips, spine, and legs. Over a 7-year journey, This bone loss would be catastrophic. Even with the most aggressive exercise regimens and pharmaceutical interventions, you'd arrive at Saturn with bones that are dangerously fragile. Muscles atrophy for similar reasons. Without the need to work against gravity constantly, muscles waste away. This isn't just about losing strength in your arms and legs. The heart is a muscle, and it weakens in microgravity. On Earth, your heart works hard to pump blood upward against gravity from your legs back to your chest. In microgravity, this isn't necessary. The heart doesn't have to work as hard, so it becomes weaker and smaller. Blood volume decreases because the body doesn't need as much. When astronauts return to Earth after even 6 months in space, they often feel dizzy and weak when standing because their cardiovascular systems have deconditioned. Some can barely stand for the first few days. For a 7-year mission, the deconditioning would be severe. Astronauts on the ISS exercise several hours every day to slow these effects. They use resistance equipment that simulates lifting weights. They run on treadmills with harnesses that pull them down against the treadmill deck, simulating body weight. They use stationary bicycles. Even with these intensive exercise regimens, they still lose bone and muscle mass. They still experience cardiovascular changes. Some of these changes reverse after returning to Earth, but not all of them. There appears to be some permanent degradation, particularly in bone density. And that's after 6 months to a year. For a multi-year journey to Saturn, the effects would be much worse, possibly severe enough that reversal becomes impossible. Your crew would arrive at Saturn weak, their bones fragile, their muscles wasted, their cardiovascular systems deconditioned and struggling. They'd have difficulty with tasks that would have been easy before the journey. Climbing a ladder, carrying equipment, even walking, if they land on a moon with significant gravity. All of this assumes the psychological challenges don't break them first. 7 years in a small spacecraft with the same handful of people. No privacy. No escape from the confined environment. No ability to step outside and experience natural environments. Fresh air, the sun on your face. Every day, the same as the last. The same walls, the same faces, the same recycled air with its faint chemical smell from the life support systems. Knowing Earth is getting farther away every day. Knowing that any emergency would be catastrophic because help is impossible. The psychological toll would be immense. We have some understanding of isolation effects from Antarctic research stations, submarines, and long-duration missions on the ISS. But a journey to Saturn would be more extreme than any of these. Antarctic researchers can leave after their term ends, usually less than a year. Submariners deploy for months, not years. ISS astronauts know they can return to Earth quickly if necessary, and they're only minutes away by radio. A Saturn crew would be truly isolated, cut off from Earth in ways that are difficult to comprehend. Communication delays grow as you travel farther from Earth. Radio signals travel at the speed of light, which sounds fast and is fast by everyday standards. But the distances involved in solar system travel are so vast that even light takes substantial time to cross them. At Saturn's average distance from the Sun, light takes about 71 to 84 minutes to travel one way, depending on where Earth and Saturn are in their respective orbits. When Earth and Saturn are on the same side of the Sun, relatively close together in solar system terms, the distance is minimized, and signals take about 71 minutes one way. When they're on opposite sides of the sun, the distance maximizes and signals take about 84 minutes one way. This means a round-trip communication time of between 2.4 and 2.8 hours. You can't have a real-time conversation with mission control. You can't call home and talk to your family the way you would on a phone call. Every interaction is delayed, asynchronous, like exchanging very slow emails. Imagine trying to troubleshoot a problem with this kind of delay. Something goes wrong with your spacecraft's oxygen generation system. Carbon dioxide levels are rising. You need help. You send a message to Mission Control, describing the problem in as much detail as possible. Then you wait. 70 to 80 minutes later, your message reaches Earth. The ground team analyzes the problem, consults documentation, maybe runs simulations, and formulates a response. This might take an hour or more, depending on the complexity of the issue. They send their response. Another 70 to 80 minutes in transit. By the time you receive their recommendations, 2.5 to 3 hours or more have elapsed since you first reported the problem. If their solution doesn't work, or if you need clarification, another round of back and forth adds another 3 hours. A troubleshooting session that would take 30 minutes with real-time communication stretches across most of a day. For critical emergencies, where you have minutes or hours to act, this delay makes Earth-based support almost useless. You're on your own. You have to solve problems with whatever knowledge and resources you have on board. The isolation would be psychologically crushing. You could send video messages to your family, but their responses would arrive hours later. You'd watch your children grow up in delayed video clips, missing birthdays and holidays by the time the messages reached you. You'd hear about family emergencies days after they happened, unable to provide support or comfort in real time. The disconnect between your experience and life on Earth would grow wider with each passing month. Your reference points would shift. Events that seem important on Earth, political developments, cultural moments, news stories, would feel distant and irrelevant. You'd be living in a different world, a small bubble of metal and plastic hurtling through the void, and Earth would become increasingly abstract. And the isolation increases as you get closer to Saturn because the planets are moving in their orbits. The distance between Earth and Saturn changes continuously. When you're halfway through your journey, you might be crossing the orbital paths at a point where Earth and Saturn are on opposite sides of the Sun, maximizing the distance. Communication delays might stretch to 90 minutes or more one way. By the time you arrive at Saturn, if Earth happens to be on the far side of the Sun, you're as isolated as it's possible to be while remaining in the same solar system. Your crew would be functionally alone, cut off from humanity in a way that's hard to fully grasp until you experience it. Every astronaut who's flown in space describes a profound sense of isolation when they look back at Earth and see it as a small blue marble suspended in blackness. For a Saturn crew, Earth would eventually become just another bright star, indistinguishable from other stars, except that they'd know which one it was. The psychological impact of this isolation cannot be overstated. Humans are social creatures. We evolved in groups, in communities, where we could see and interact with dozens or hundreds of other people regularly. Even introverts, people who need solitude to recharge, still need some social interaction. A crew of 5 or 6 people locked in a spacecraft for 7 years would be at the extreme edge of what humans can psychologically endure. Studies of small, isolated groups show that conflicts emerge over time. Small annoyances become major irritations. Personality quirks that seemed minor at first become unbearable. Cliques form. People stop communicating effectively. In extreme cases, crews have become dysfunctional, with members refusing to work together or actively sabotaging each other. This has happened in Antarctic stations, where people had much more space and better conditions than a spacecraft provides. For a Saturn mission, crew selection and psychological support would be absolutely critical. You'd need people who are not just technically competent, but also psychologically resilient, compatible with each other, able to manage stress and conflict effectively. You'd probably want to send people who have strong personal relationships, maybe married couples or close friends who've worked together for years. But even with the best selection and training, 7 years is a long time. People change. Relationships evolve. What works at the beginning of the mission might not work at the end. The spacecraft would need private spaces, areas where crew members could have time alone. It would need recreational facilities, entertainment systems, perhaps virtual reality to provide simulated experiences of nature and different environments. It would need excellent communication systems, so crew could maintain relationships with people on Earth as much as the time delay allows. All of this adds complexity, mass, and potential failure points to an already incredibly complex mission. But suppose you solve all these problems. Suppose you develop the technology for long-duration life support systems that can recycle air and water with near-perfect efficiency for years. Suppose you create effective radiation shielding that keeps exposure within acceptable limits. Suppose you develop artificial gravity systems, perhaps rotating sections of the spacecraft to create centrifugal force that simulates gravity and prevents bone loss and muscle atrophy. Or suppose you develop medical countermeasures, drugs and therapies that prevent or reverse the effects of microgravity without requiring massive rotating structures. Suppose you perfect the psychological support systems, create training programs and crew selection processes that ensure psychological stability over multi-year missions. Suppose you develop better propulsion systems that reduce the transit time, maybe using nuclear electric propulsion or even fusion drives that could cut the journey from 7 years to 3 or 4. Suppose you actually solve all these immense technological challenges and successfully make the journey to Saturn. Your crew arrives intact, healthy enough to function, psychologically stable, ready to begin the mission. Now what? You still can't go home. Because Saturn itself, the destination, presents challenges that make departure extraordinarily difficult and perhaps impossible. Let's talk about what Saturn actually is. Saturn is a gas giant, the second largest planet in the solar system after Jupiter. It has an equatorial diameter of roughly 74,898 miles, or 120,536 kilometers. That's about 9.4 times Earth's diameter. Its mass is 95 times Earth's mass, though despite this enormous mass, its average density is actually less than water. If you could find a bathtub large enough, Saturn would float. This low density tells us about Saturn's composition. The planet is composed primarily of hydrogen and helium, the simplest and most abundant elements in the universe. These are the same materials that make up the Sun and most other stars. Saturn is, in essence, a failed star. If it had been about 80 times more massive, the pressure and temperature at its core would have become high enough to initiate nuclear fusion, the process that powers stars. But it fell short of that threshold. Instead of becoming a star, it became a gas giant planet. The planet has no solid surface. This is difficult for people to grasp, because every planet we're familiar with, Earth, Mars, Venus, even rocky worlds like Mercury and the Moon, they all have surfaces where you could, in principle, stand. But Saturn doesn't work that way. If you tried to descend into Saturn's atmosphere, you wouldn't find ground. There's no level where the gas ends and solid material begins. You'd sink deeper and deeper into increasingly dense, increasingly hot gas. The atmosphere would gradually thicken around you from a thin haze at the cloud tops to a dense fog deeper down. Then to a crushing pressure that would destroy any spacecraft long before you reached anything resembling a surface. Eventually, at depths of tens of thousands of miles, the pressure and temperature become so extreme that hydrogen, which is a gas at low pressure and a solid at extremely high pressure, transitions to a liquid state. Deeper still, perhaps 15,000 to 20,000 miles down, the pressure reaches millions of times Earth's atmospheric pressure. At these conditions, hydrogen transitions to a strange state called metallic hydrogen. In this state, the pressure is so high that hydrogen's electrons are stripped away from their atoms and flow freely, making the hydrogen electrically conductive like a metal. This metallic hydrogen layer is thought to be responsible for Saturn's powerful magnetic field. Electric currents flowing in this conducting fluid generate magnetic fields through the same dynamo process that generates Earth's magnetic field, just on a vastly larger scale. No spacecraft humanity has ever built could reach Saturn's metallic hydrogen layer. You'd be crushed and incinerated long before getting there. At the core, below all these layers of atmosphere and liquid and metallic hydrogen, there's probably a dense central region. This core is thought to be composed of rock, metal, and exotic high-pressure forms of ice, water ice, ammonia ice, methane ice, all compressed to densities far higher than anything found on Earth's surface. The core might be 10 to 20 times Earth's mass, though it's difficult to determine precisely because we can't see it or directly measure it. Our understanding comes from modeling Saturn's gravity field and how the planet responds to gravitational perturbations. Temperatures at Saturn's core are estimated at somewhere between 20,000 and 25,000 degrees Fahrenheit, or 11,000 to 14,000 degrees Celsius. For comparison, the Sun's visible surface is about 10,000 degrees Fahrenheit. Saturn's core is hotter than that. The pressure at the core is estimated at tens of millions of times of the Earth's sea level atmospheric pressure. At these extreme conditions, matter behaves in ways that are difficult to study because we can't replicate these conditions in laboratories. Materials that are soft and weak at normal pressures become incredibly hard. Chemical reactions that don't occur at normal conditions become favorable. The physics is fascinating, but also means that nothing we've ever built could survive those conditions. No material, no design, no clever engineering solution can withstand tens of millions of atmospheres of pressure and tens of thousands of degrees of temperature. The forces involved are simply too immense. So you can't land on Saturn because there's nothing to land on. You could descend into the atmosphere, but you'd be destroyed by heat and pressure within hours at most, probably much sooner. The Galileo probe, which descended into Jupiter's atmosphere in December 1995, survived for about 58 minutes and transmitted data from a depth where the pressure was about 24 times Earth's atmospheric pressure and the temperature was about 330 degrees Fahrenheit, or 166 degrees Celsius. Then it was crushed and vaporized. Saturn's atmosphere is somewhat less extreme than Jupiter's at comparable depths, but the principle is the same. Any descent is one way. You can send a probe to gather data for an hour or two before it's destroyed, but you can't send humans and expect them to return. And there's another danger we haven't fully addressed yet: the rings themselves. Saturn's rings are one of the most beautiful features in the solar system. They're also a navigation hazard and a source of potential danger that people often don't fully appreciate. The rings aren't solid structures. They're made up of billions of individual particles ranging from dust grain size to chunks as large as houses or small mountains. Most of the ring material is water ice, very pure ice, which is why the rings are so bright and reflective. But there are also rocky particles mixed in, silicates and other materials. All of these particles orbit Saturn in a disk only about 30 feet thick, in most places, despite extending more than 175,000 miles from the planet's cloud tops. That's an incredibly flat structure. If you scaled the rings down so they were as wide as a football field, they'd be thinner than a sheet of paper in most places. The thinness is maintained by gravitational interactions between the particles and by the gravitational influence of Saturn's moons. The particles collide gently, settling into the thinnest possible configuration, like sediment settling in water. But this means the rings are a very dense environment if you're trying to fly through them. The particles are orbiting Saturn at different speeds, depending on their distance from the planet. Inner ring particles orbit faster. Outer ring particles orbit slower. The relative velocities between particles at different distances can be substantial, thousands of miles per hour. If your spacecraft passes through the ring plane, you're potentially encountering particles traveling at high velocities relative to you. A collision with even a small particle at orbital velocities can be catastrophic. A pebble-sized chunk of ice hitting your spacecraft at 10,000 miles per hour carries enormous kinetic energy. It would punch through thin metal like a bullet through paper. It could shatter windows, breach pressure vessels, damage critical systems. Cassini carefully avoided flying through the densest parts of the rings for most of its mission. It orbited at angles that minimized ring plane crossings. Only at the very end of the mission, in its final orbits, did Cassini deliberately fly through the gap between Saturn's atmosphere and the innermost edge of the rings. This was the grand finale, a series of 22 orbits that took Cassini places no spacecraft had been before. The gap between Saturn and the rings is only about 1,500 miles wide. For context, Saturn's diameter is about 75,000 miles. So this gap is only about 2% of Saturn's diameter. Flying through it required extraordinary precision. Cassini had to hit a very narrow corridor, threading between the planet's upper atmosphere below and the ring particles above. The spacecraft encountered more dust particles in this region than expected. Tiny ring particles that had drifted inward, creating a faint, dusty environment even in the gap. These dust impacts were detected by instruments and caused slight changes in the spacecraft's attitude as the particles hit. For a crewed mission, the rings present a serious navigational challenge. You can't just approach Saturn from any direction. You have to plan your trajectory to minimize time spent in the ring plane and to avoid the densest regions. This constrains your mission design. It limits when you can launch, based on where Saturn is in its orbit and what approach angles are available. It affects which moons you can easily reach, because some require crossing the ring plane multiple times. And if something goes wrong, if you have a propulsion failure or navigation error that sends you through the rings instead of avoiding them, you could be destroyed. The rings are also electrically charged. The charged particles from Saturn's magnetosphere interact with the ring particles, creating complex electromagnetic environments. There are spoke-like features in the B ring, mysterious radial structures that appear and disappear, possibly caused by electromagnetic forces levitating tiny dust particles above the main ring plane. These spokes were first observed by Voyager and later by Cassini. We still don't fully understand what causes them or exactly how they form. If your spacecraft passes through these regions, you might experience electromagnetic interference. Your communications could be disrupted. Your instruments might give false readings. In extreme cases, electrical discharges might damage sensitive electronics. These are risks that can be managed with careful planning, but they add complexity to an already complex mission. The rings also create navigation uncertainty. The gravitational field near Saturn is influenced not just by the planet itself, but by the distribution of mass in the rings. The rings contain a lot of mass, roughly equivalent to one of Saturn's medium-sized moons distributed across that huge disk. This mass creates gravitational perturbations that affect spacecraft trajectories. When you're navigating close to Saturn, you have to account for these perturbations. Your trajectory calculations become more complex. The uncertainties in your position and velocity grow slightly because you're dealing with a more complicated gravitational field. For most purposes, this is manageable. Cassini navigated successfully for 13 years. But for a crewed mission, where precision matters even more because humans are aboard, every additional source of uncertainty is concerning. And then there's the sheer scale of the ring system to consider. The main rings extend from about 4,300 miles above Saturn's cloud tops out to about 85,000 miles. Beyond that are the fainter outer rings, gossamer structures that extend much farther. The E-ring, created by material from Enceladus's geysers, extends from about 112,000 miles out to 360,000 miles from Saturn. This is a huge volume of space filled with particles. Any mission operating in the Saturn system will spend time in or near this environment. You can't avoid it entirely. And every time you pass through the ring plane, even in the thinner regions, you're taking a calculated risk. The radiation environment near the rings is also more complex than in empty space. The ring particles interact with charged particles from Saturn's magnetosphere. Some radiation gets absorbed by the rings, creating a partial radiation shadow. But other radiation processes create new charged particles. Cosmic rays hit ring particles, creating showers of secondary particles. The electromagnetic interactions create plasma and accelerate particles to high energies. The net effect is that the radiation environment near the rings is different from the environment farther away. It's not necessarily worse, but it's more variable and less predictable. For mission planning, this means you can't just use simple models of Saturn's radiation environment. You have to account for the rings and how they modify the particle populations. This requires more sophisticated modeling and more uncertainty in your predictions. What about Saturn's moons? Saturn has 83 known moons, and probably more small ones that haven't been detected yet. These moons range from tiny, irregular chunks of rock and ice, mere miles across, barely more than captured asteroids, to Titan, which is larger than the planet Mercury and is one of the most Earth-like bodies in the solar system, despite being nearly 1 billion miles from the Sun. Surely you could land on one of the moons, explore, gather data, conduct science missions, and then use the moon as a base for your return journey to Earth. This is more plausible than trying to interact directly with Saturn. The moons have solid surfaces where you could actually land. They have gravity, weak compared to Earth, but enough to keep you from drifting away. They provide potential resources, water ice that could be melted for drinking water or split into hydrogen and oxygen for propellant. Some of them are scientifically fascinating. Titan, the largest moon, has a thick nitrogen atmosphere, thicker than Earth's, with surface pressure about 1.5 times Earth's sea level pressure. It has lakes and rivers of liquid methane and ethane. It has weather, clouds, rain, seasonal changes. It has complex organic chemistry happening in its atmosphere and on its surface that might give us clues about the chemistry that led to the origin of life on Earth. Enceladus, one of the smaller major moons, has geysers erupting from cracks near its south pole. These geysers shoot water ice and organic molecules into space at high velocity. Cassini flew through these plumes and analyzed their composition, finding evidence of a subsurface ocean beneath Enceladus's icy crust. This ocean is in contact with the moon's rocky core, meaning there could be hydrothermal activity, chemical energy sources, and all the ingredients necessary for life as we know it. If there's life anywhere in the solar system beyond Earth, Enceladus is one of the top candidates. Other moons like Dione, Rhea, and Iapetus have their own interesting features. Strange surface markings, ancient impact craters, mysterious brightness variations. But landing on Saturn's moons doesn't solve the fundamental problem of getting back to Earth. In fact, in some ways, it makes the problem worse. Here's why. Getting to Saturn requires enormous amounts of energy. You have to accelerate your spacecraft to high velocity, tens of thousands of miles per hour, to make the journey in a reasonable time frame. 7 years is already a long time. If you used less propellant and a slower trajectory, the journey could take 10 or 15 years, or even longer. Nobody wants a 15-year journey each way, so you need to go fast. Going fast requires energy, which in rocket terms means propellant. When you arrive at Saturn, you're moving very fast relative to the planet. If you do nothing, you'll just fly past and continue into the outer solar system, which doesn't help. To go into orbit around Saturn or land on one of its moons, you need to slow down. This requires firing your engines in the direction you're traveling, using your propellant to reduce your velocity. This is called a capture burn, or orbital insertion burn, and it requires a lot of propellant. If you're planning to land on a moon, you need even more. You slow down to enter Saturn orbit, then slow down more to match the moon's orbit, then slow down more to descend to the surface. Every bit of this requires propellant. And here's where the physics becomes cruel. That propellant has mass. And that mass has to be carried all the way from Earth. To carry more propellant, you need a bigger rocket. But a bigger rocket with more propellant has more mass. More mass requires more propellant to accelerate, which increases mass further, which requires even more propellant. The rocket equation, as we discussed earlier, compounds exponentially. For a one-way mission like Cassini, this is manageable. You use all your propellant budget for the journey out and for operations at Saturn. You don't need to save anything for a return trip because you're not coming back. For a crewed mission that needs to return, you face a much more difficult problem. You need propellant for the journey to Saturn. You need propellant for capture into Saturn orbit. You need propellant for operations around Saturn, moving between moons, adjusting orbits. You need propellant to lift off from a moon's surface if you land. You need propellant to escape from Saturn's gravity well. And you need propellant for the journey back to Earth. All of this propellant has to be carried from Earth, or you need to manufacture it at Saturn using local resources, which we'll discuss shortly. If you're carrying all the return propellant from Earth, the mass of your spacecraft at launch becomes astronomical. Let's run rough numbers to see how this works. Suppose your spacecraft has a dry mass, the mass of the structure and equipment without propellant, of 100 tons. That's probably optimistic for a crewed interplanetary spacecraft with all necessary systems, but let's use it. Chemical rockets, the type we currently use, have specific impulses around 300 to 450 seconds, depending on the propellant combination. Specific impulse is a measure of rocket efficiency, how much thrust you get per unit of propellant. Using the rocket equation, if you want to achieve a velocity change of, say, 10 kilometers per second, which is roughly what you'd need for various phases of a Saturn mission, you'd need about 4.6 times the dry mass in propellant. So, 100 tons of spacecraft needs 460 tons of propellant. That's your spacecraft mass, before the first burn, 560 tons. But you need multiple burns. One to leave Earth orbit. One to adjust your trajectory mid-course. One to capture at Saturn. Multiple smaller burns for operations. One to leave Saturn. One to capture at Earth on return. Each burn requires propellant, and the propellant for later burns has to be carried during earlier burns, adding to the mass that must be accelerated. When you work through the math carefully, the numbers explode. A crewed Saturn mission, using chemical propulsion and carrying all propellant from Earth, would require launching thousands of tons into orbit. The launch costs alone, at current prices of roughly $10,000 per kilogram to orbit, would run into tens of billions of dollars just for the propellant. That's before you count the cost of the spacecraft itself, the development costs, the operations costs, the ground support infrastructure. You're looking at a mission that would cost several $1 trillion. For comparison, the International Space Station, the most expensive single object ever built, cost roughly $150 billion over its development and construction phase. A crewed Saturn mission might cost 10 to 20 times that. The economic case is difficult to make. One way to reduce the propellant requirement is to use more efficient propulsion systems. Nuclear electric propulsion, or ion drives, can achieve much higher specific impulses than chemical rockets, sometimes 10 times higher or more. This reduces the propellant mass significantly. But these systems have their own problems. They produce very low thrust, so acceleration is gradual. A journey that takes 7 years with chemical rockets might take similar or even longer with ion drives, though the propellant savings would be substantial. The technology is also less mature. We've flown ion drives on robotic missions, but never at the scale needed for a crewed interplanetary spacecraft. Another approach is in situ resource utilization, the idea of manufacturing propellant at your destination using local materials, rather than carrying all propellant from Earth. This is theoretically possible and is a key part of many Mars mission concepts. For Saturn, the idea would be to land on a moon like Enceladus or Titan, extract water or hydrocarbons, and manufacture fuel from these local materials. Water can be electrolyzed, split using electricity into hydrogen and oxygen. Both are excellent rocket propellants. Liquid hydrogen and liquid oxygen are what the space shuttle main engines used. Methane and oxygen also make a good propellant combination, and Titan has abundant methane. But the equipment needed to extract, process, and store these materials is massive, complex, and has never been demonstrated at the scale required for a crewed interplanetary mission. You'd need power sources, probably multiple nuclear reactors, generating hundreds of kilowatts or even megawatts of electricity. Solar panels won't work well at Saturn's distance from the Sun. The sunlight there is only about 1% as intense as it is at Earth, so you'd need massive solar arrays to generate meaningful power, and they'd be vulnerable to damage from micrometeoroids and radiation. Nuclear is the only practical option. You'd need chemical processing plants, equipment to drill or mine ice, pumps to move liquids, electrolyzers to split water, compressors to pressurize gases, cryogenic storage tanks to keep hydrogen and oxygen, or methane and oxygen, at the extremely cold temperatures required to keep them liquid. You'd need all of this equipment to operate reliably in Saturn's harsh radiation environment at temperatures that can drop to -300 degrees Fahrenheit or colder. And you'd need redundancy because a single critical failure could strand you. If the oxygen production system breaks and you can't fix it, you can't make propellant. If you can't make propellant, you can't leave. Building this infrastructure on a Saturn moon would be an enormous undertaking. It might require multiple cargo missions sent ahead of the crew to pre-position equipment. Robots or earlier crews would need to set up the systems, test them, and begin producing propellant before the main crew arrives. This adds years to the mission timeline and multiplies the cost. Each cargo mission requires its own launch, its own propellant, its own flight through deep space. You might need 5 or 10 cargo flights before the crewed mission even launches, and there's no guarantee it will work. In situ resource utilization has never been done on another world. We've never drilled for ice on the Moon or Mars. We've never operated chemical plants on airless moons in deep space. We've never stored cryogenic propellants for months or years in the space environment. All of this is technically possible in theory, but theory and practice are different. Systems that work perfectly in laboratory tests often fail in real-world conditions. Space is unforgiving. There's no room for trial and error when your crew's lives depend on the systems working. Even assuming you can do all this, you're looking at a surface stay of months or years while you manufacture enough propellant for departure. Producing tons of liquid hydrogen and oxygen, or methane and oxygen, takes time. Electrolysis isn't instantaneous. You can only produce propellant as fast as your power systems and processing equipment allow. If you're generating a few kilograms per day, and you need tens of tons for the return journey, you're looking at years of operation. During this time, your crew is living on an airless, frozen moon, exposed to Saturn's radiation belts, dependent on systems that have to work perfectly because there's no rescue option. They're in habitats that have to maintain pressure, provide breathable air, recycle water, grow or store food, and protect them from radiation and temperature extremes. The habitats have to function flawlessly for years. Any failure in critical systems, life support, power, thermal control, could be catastrophic. The psychological impact of knowing you're committed, that you can't leave until the fuel is ready, that any critical failure means you're stranded nearly 1 billion miles from home with no hope of rescue, would be immense. Every day, you'd wake up knowing that Earth is unreachably far away, that if something goes wrong, you die, that your survival depends entirely on machines continuing to function and your own ability to repair them when they inevitably break down. The stress would be extraordinary. Some people might handle it well. Others might break down mentally, become depressed, anxious, unable to function. And you can't send them home early. There's no evacuation option. They have to endure until the propellant is ready. Let's talk more specifically about Saturn's radiation environment, because this is one of the less discussed but more serious hazards. Saturn has a strong magnetic field, about 578 times stronger than Earth's magnetic field. This is generated, as mentioned earlier, by electric currents in the metallic hydrogen layer deep inside the planet. The magnetic field extends far into space, creating a magnetosphere that traps charged particles from the solar, wind, and cosmic rays. These trapped particles bounce back and forth between Saturn's magnetic poles, creating radiation belts similar to Earth's Van Allen belts, but much more intense and much larger. The radiation is concentrated near Saturn's equatorial plane, which is also where the rings are. The rings and many of the larger moons orbit in this equatorial plane, right in the heart of the radiation belts. The radiation extends outward from Saturn's cloud tops to beyond the orbit of Titan, Saturn's largest moon. Titan orbits at about 759,000 miles, or 1.22 million kilometers, from Saturn's center. Even at this distance, radiation levels are significant, though Titan's thick atmosphere provides some shielding. Spacecraft passing through these radiation belts are bombarded with high-energy protons and electrons. These particles have energies ranging from thousands to millions of electron volts. When they strike spacecraft surfaces, they cause damage. They can penetrate electronics, flipping bits in computer memory and causing malfunctions. They degrade materials, causing them to become brittle or to outgas, releasing trapped gases that can contaminate sensitive optical surfaces. Over time, this radiation damages spacecraft systems, reducing their operational lifetime. Cassini was designed with radiation hardening, special shielding around its sensitive electronics, and careful selection of radiation-resistant components. Even so, it accumulated damage over its 13-year mission. Engineers had to carefully plan Cassini's trajectory to minimize time spent in the most intense parts of the radiation belts. Some scientific observations couldn't be performed because getting close enough would have exposed the spacecraft to radiation levels that would have shortened its mission unacceptably. A crewed spacecraft would need much more extensive shielding than Cassini. Humans are more sensitive to radiation than electronics. While you can design radiation-hardened chips that tolerate high radiation doses, human cells are vulnerable at much lower levels. The spacecraft would need thick shielding around crew quarters, probably multiple feet of water or polyethylene or other hydrogen-rich materials. This adds enormous mass. Water is heavy. A cubic meter of water weighs 1 ton. If you need a meter-thick water shield around a habitat module, and the module has a surface area of, say, 100 square meters, you need 100 tons of water just for shielding. And a meter might not be enough for long-term protection in Saturn's radiation belts. This shielding mass has to be launched from Earth or manufactured from local resources at enormous effort. And even with shielding, some radiation gets through. High-energy particles interact with the shielding material, creating secondary radiation and neutrons. You can reduce radiation exposure, but you can't eliminate it. If you're operating near Saturn for an extended period, conducting surface operations on Enceladus, or orbiting between moons studying the Saturn system, your cumulative radiation exposure climbs steadily. There's no escaping it. Even inside a well-shielded spacecraft or habitat, radiation is getting through at levels that increase cancer risk and cause tissue damage. This isn't an immediate, acute effect. You won't get radiation sickness from chronic low-level exposure. But over months and years, the damage accumulates. DNA is damaged in cells throughout your body. Most of this damage is repaired by cellular repair mechanisms, but some isn't. Some damaged cells become cancerous. Some die, reducing the functional capacity of tissues and organs. Your risk of developing cancer later in life increases significantly. Your immune system function may decline. You may develop cataracts earlier than you would otherwise. There's also emerging evidence from studies of astronauts and from animal experiments that radiation exposure might affect the brain. High-energy particles passing through the brain can damage neurons, potentially affecting memory, cognition, and decision-making ability. The effects are subtle and not fully understood, but they're concerning for long-duration deep space missions, where crew members need to make critical decisions and perform complex tasks. If radiation exposure is degrading their cognitive function, even slightly, it increases the risk of errors and accidents. Titan is an interesting case because its thick atmosphere provides natural radiation shielding. The atmosphere is about 1.5 times as dense as Earth's atmosphere at sea level. It's composed mostly of nitrogen, about 98%, with about 1.5% methane and traces of other gases. This thick atmosphere absorbs many of the charged particles from Saturn's radiation belts. If you're on Titan's surface, inside a habitat, or wearing a spacesuit, you get significantly less radiation than you would in orbit around Saturn or on an airless moon like Enceladus or Rhea. This makes Titan one of the safer places in the Saturn system from a radiation perspective. But Titan has its own challenges that make it a difficult place to live and work. The surface temperature on Titan is about -290 degrees Fahrenheit or -179 degrees Celsius. This is cold enough that water ice is as hard as rock. If you hit water ice with a hammer on Titan, it would shatter like granite. Methane and ethane, which are gases at Earth's temperatures, are liquids on Titan. The lakes and rivers you see in images of Titan aren't water. They're liquid methane and ethane, possibly with dissolved nitrogen and other hydrocarbons. These hydrocarbons rain from the sky, collect in river valleys, and flow into lakes and seas. Titan has a hydrological cycle similar to Earth's water cycle, except it's based on methane instead of water. Clouds form in Titan's atmosphere when methane vapor condenses. Methane rain falls. It collects on the surface and eventually evaporates back into the atmosphere, completing the cycle. Operating in this environment requires equipment designed for extreme cold. At -290 degrees Fahrenheit, many materials behave differently than they do at room temperature. Metals that are ductile and tough at room temperature become brittle. If you try to bend a piece of aluminum or steel at Titan temperatures, it might snap rather than bending. Plastics lose their flexibility and can shatter. Rubber seals become hard and inflexible, potentially losing their ability to seal properly. Lubricants freeze solid, causing moving parts to seize. Even electronics behave differently. Some components improve at low temperatures, less thermal noise, lower resistance in conductors. But others fail. Batteries lose capacity. Liquid crystal displays stop working. Some semiconductors change their properties. Every system on your spacecraft and in your habitat has to be designed for these extreme conditions and tested extensively. You can't just take equipment designed for Earth and expect it to work on Titan. And Titan's atmosphere, while useful for radiation shielding, is chemically reactive in ways that create additional challenges. Ultraviolet light from the sun, weak at Saturn's distance but still present, breaks down methane molecules in Titan's upper atmosphere. The fragments recombine in complex ways, forming larger organic molecules, things like ethane, propane, acetylene, benzene, and even more complex compounds. These organic molecules are collectively called tholins, a term coined by astronomer Carl Sagan to describe the complex organic haze that gives Titan's atmosphere its orange color. Tholins are scientifically fascinating because they're similar to the organic compounds that might have been present on early Earth before life emerged. Studying Titan's atmospheric chemistry could give us insights into prebiotic chemistry and the origins of life. But from an engineering perspective, tholins are a problem. They rain down onto Titan's surface as a kind of organic smog, coating everything. If you have a solar panel or a window or any optical surface, it will gradually get coated with tholin deposits. This reduces the amount of light getting through, which is already a problem at Saturn's distance from the Sun. Mechanical systems with exposed moving parts could get gummed up with tholin deposits. Air filters in your habitat might clog with tholins if there's any leakage from outside. You'd need regular maintenance to clean surfaces and replace filters, and you'd need to design systems that are tolerant of contamination. Any breach in your spacesuit or habitat would expose you to Titan's atmosphere. You can't breathe it. It's almost all nitrogen with some methane, no oxygen. You'd suffocate within minutes. The cold would kill you even faster. At -290 degrees Fahrenheit, exposed skin would freeze almost instantly. Your lungs would freeze if you tried to breathe. Even with the best possible equipment and preparation, operations on Titan would be extraordinarily difficult and dangerous. Your spacesuits would need to be heated, insulated to prevent heat loss to the frigid environment. This requires power, batteries, or small nuclear generators. If your suit's heating system fails, you have minutes at most before hypothermia sets in. You'd need redundant systems, backup heaters, emergency procedures, and you'd need to be extremely careful about any situation that could lead to a suit breach. On Earth, a small tear in a spacesuit in a vacuum is serious but manageable. You lose air pressure, but you have time to get to an airlock. On Titan, a breach means you're exposed to an atmosphere you can't breathe and temperatures that would kill you in seconds. There's much less time to react. Let's think about what happens if something goes wrong during a Saturn mission. Any of the thousands of things that could go wrong. On Earth, if you have a medical emergency, help can arrive within hours. Ambulances, helicopters, rapid response teams. If a spacecraft malfunctions in Earth orbit, you can abort to the ground or send up a rescue mission within days. The infrastructure exists. launch pads, rockets, trained crews. On the International Space Station, if a critical system fails and can't be repaired, the crew can evacuate in Soyuz or Crew Dragon capsules and return to Earth within hours. They undock, perform a deorbit burn, and land. It's a tested, reliable procedure. At Saturn, there is no rescue. None. If someone gets sick or injured beyond your crew's medical ability to treat, they die. If a critical system fails and you don't have spare parts or can't repair it, you die. There's no calling for help. No evacuation. No backup plan that results in anyone coming to save you. Earth is over an hour away, by radio signals traveling at the speed of light. By spacecraft, even with the fastest propulsion systems we can currently imagine, Earth is years away. If you sent a distress call today, and Earth immediately organized a rescue mission using the fastest spacecraft available, that rescue mission would take years to reach you. 3 years if they use high-energy trajectories and advanced propulsion. More likely, 5 to 7 years with realistic technology. By the time help arrives, everyone would be long dead, either from the initial problem or from starvation when food runs out, or from life support failure, or from any of 100 other ways you can die in space when critical systems stop working. You're on your own. Completely and absolutely. This changes the calculus of risk in fundamental ways. Every decision has to be made with the knowledge that there's no safety net. No one is coming to save you. You have to save yourself or you die. Medical screening for crew would need to be extraordinarily thorough. You can't have someone develop a serious health problem during the mission. You'd screen for genetic predispositions to cancer, heart disease, any condition that might manifest over a multi-year time frame. You'd want younger crew members because the statistical risk of serious health problems increases with age. But you also want experienced crew, people who've proven they can handle the stress and challenges of spaceflight. This creates tension in crew selection. Equipment redundancy would need to be extreme. Every critical system needs backups, probably multiple backups. If your primary oxygen generation system fails, you need a secondary system that can take over immediately. If that fails, you need tertiary backups, maybe chemical oxygen generators that can provide emergency oxygen for days or weeks while you repair the primary systems. The spacecraft becomes heavier and more complex with all these redundant systems, but the alternative is accepting that a single-point failure kills everyone. That's not acceptable. The crew would need training in every system, every repair procedure, every contingency. They can't rely on specialists on the ground to guide them through problems with multi-hour communication delays. They need to be able to diagnose faults, understand schematics, improvise repairs with available materials. They need to be generalists, capable of working on life support, power systems, propulsion, communications, computing, everything. This is a much higher level of competence than required for current spaceflight. ISS astronauts specialize. One might be an expert in robotics, another in life support systems, another in scientific experiments. They have mission control, providing continuous support, guidance, troubleshooting. A Saturn crew couldn't work that way. Everyone needs to know everything, or at least enough to keep critical systems running. The level of autonomy and competence required is beyond anything we've attempted in human spaceflight so far. Even the Apollo astronauts, who traveled farther from Earth than anyone before or since, were only seconds away by radio and days away by spacecraft. They had mission control monitoring every parameter, analyzing data, providing solutions. When Apollo 13 suffered an explosion that crippled the spacecraft, the crew worked with mission control for hours to devise a solution. Engineers on the ground ran simulations, tested procedures, calculated trajectories. The crew executed the plan. Mission control developed. It was a collaborative effort, and it saved their lives. Your Saturn crew would have guidance from Earth, but it would be delayed, asynchronous, ultimately limited. They'd receive suggestions and recommendations, but they'd have to make critical decisions in real time without the ability to consult Earth and get an immediate response. They'd have to trust their own judgment, their own expertise, their own improvisation skills. If they make the wrong decision, they die. The weight of that responsibility, the knowledge that your survival depends entirely on your own actions and those of your small crew, would be psychologically crushing for some people. Now, let's talk about the return journey itself, assuming you make it that far. Suppose you've done everything right. You've reached Saturn safely, despite the long journey and accumulated radiation exposure. You've conducted your mission, explored moons, gathered scientific data, maybe even found evidence of life in Enceladus's subsurface ocean. You've manufactured or conserved enough fuel for departure through in-situ resource utilization or careful mission planning, and you're ready to come home. You fire up your engines, escape from the moon's gravity, escape from Saturn's massive gravity well, and begin the long journey back toward the inner solar system. You're going home. Except you still face a journey that's just as long and just as dangerous as the trip out. Another 7 years or so in space, depending on your trajectory and propulsion system. Another 7 years of radiation exposure on top of what you've already accumulated. Another 7 years of microgravity effects, or partial gravity, if you have artificial gravity systems, but even partial gravity doesn't fully prevent bone loss and muscle atrophy. Another 7 years of isolation and confinement. Another 7 years of breathing, recycled air, drinking recycled water, eating stored or hydroponically grown food. But this time, there are additional complications. Your spacecraft and equipment have been operating for years already. They've been exposed to years of radiation, which degrades electronics and materials. They've experienced thermal cycling, repeated heating and cooling as the spacecraft passes through sunlight and shadow, or as internal systems turn on and off. This causes materials to expand and contract, creating mechanical stress that can lead to fatigue failures over time. They've been exposed to micrometeorites, tiny particles of dust and debris that travel through space at high velocities. These particles are small, typically less than a millimeter across, but at orbital velocities of tens of thousands of miles per hour, they hit with tremendous force. Over years of exposure, micrometeorite impacts accumulate. They pit surfaces, create tiny holes in thin materials, potentially damage sensitive equipment. You're asking all this equipment, already aged and worn, to work for another 7 years under the same harsh conditions. Systems that were new and fresh at launch are now old. Seals made of rubber or plastic might be degrading, becoming brittle, losing their ability to maintain pressure. Electronics might be showing damage from radiation, subtle bit flips in memory, degraded performance in processors and sensors. Mechanical systems might have more friction or play in their joints, wear in bearings, fatigue in structural members. Consumables, like filters, absorbent materials in life support systems, are near end of life or already used up. You've replaced them with spares, but you might be running low on spares. Every critical component that fails during the return journey is a potential mission-ending problem. You don't have access to resupply from Earth. You don't have the ability to manufacture complex replacement parts unless you brought along sophisticated fabrication equipment like 3D printers capable of making precision components. If a critical component fails and you don't have a spare and can't improvise a repair, you're in serious trouble. And you're doing all this with a crew that's already compromised. After years at Saturn, after the stress of surface operations or orbital science missions, after exposure to years of radiation and time in microgravity or partial gravity, your crew isn't in the same condition they were when they left Earth. They're older. 14 years older by the time they return. If the round trip takes 14 years, that's a significant fraction of a human lifespan. People who left Earth in their 30s would return in their mid-40s. People who left in their 40s would return nearing 60. They've aged while their families and friends back on Earth have also aged. Their children, if they had young children when they left, would be teenagers or young adults. Siblings would be noticeably older. Parents might have passed away. The world they return to won't be the world they left. They're more fatigued, both physically and mentally. The accumulated stress of years in space, the constant vigilance required to maintain systems and ensure survival, the psychological toll of isolation, all of this wears on people. They might be dealing with health issues, chronic conditions that developed during the mission, radiation-induced problems that are starting to manifest, bone density loss that's reached the point where fractures become a serious risk, muscle atrophy that makes physical tasks difficult. The return journey would be harder than the outbound journey, not easier. Not just because the equipment is older and more worn, but because the crew is less capable of handling the challenges. They're tired. They're worn down. They want to be home, and the knowledge that they still have years to go before they arrive might be demoralizing. And consider what's happening on Earth while you're gone. The mission launched perhaps 2 years before you reach Saturn, accounting for planning and travel time. You spent 2 or 3 years at Saturn conducting operations and manufacturing propellant. You've been traveling back for several years. Total time since launch, 14 to 16 years. Possibly longer if there were delays. That's a huge amount of time in human terms. A substantial fraction of most people's professional careers. The political landscape has changed. Administrations have turned over multiple times. The space agencies or corporations that sent you might have different leadership, different priorities, different budgets. Politicians who championed the mission and secured funding might be out of office. Their successors might have different priorities. Public interest in the mission might have waned. Initially, when you launched, the mission was news. People watched the departure, followed the journey, celebrated your arrival at Saturn. But 14 years is a long time to maintain public interest in anything. People's attention shifts. New priorities emerge. Unless you're continuously sending back spectacular discoveries, life-changing findings, the kind of results that make headlines and excite the public, interest fades. And even if you do send back spectacular results, after a few years, even spectacular becomes routine. The first images of Titan's surface were exciting. The 10th batch of images, less so. By the time you're returning, you're old news. A mission from a previous era that people have mostly forgotten about. Funding might be uncertain. The ground support infrastructure that was built to support your mission, the tracking antennas, the mission control centers, the teams of engineers and scientists dedicated to your mission might have been repurposed or shut down to save costs. Maintaining this infrastructure for 14+ years is expensive. Budgets are always tight. There's pressure to cut costs, to redirect funds to newer missions, to current priorities. If support for your mission collapses halfway through or during the return journey, you're in a difficult position. You're still out there, still dependent on ground support for communications, for navigation updates, for guidance and troubleshooting assistance. You're still expecting that when you return to Earth, there will be recovery teams ready to retrieve you, medical facilities prepared to handle crew that's been in space for 14 years, rehabilitation programs to help you readjust to life on Earth. But if the political and public support isn't there, if budgets have been cut, if attention has moved on to other things, the infrastructure to support your return might be minimal or absent. This is a nightmare scenario, and it's not entirely unrealistic. Long-term commitments in space exploration are fragile. They depend on continued funding, which depends on political will, which depends on public interest. All of these can evaporate faster than a spacecraft can travel to Saturn and back. We've seen this happen before with other programs. Skylab, the first American space station, was launched in 1973. It was occupied by 3 different crews over the course of 1973 and 74. Then, it was abandoned because NASA shifted priorities to the Space Shuttle program. Skylab remained in orbit, unused, until it re-entered the atmosphere and broke up in 1979. The Soviet Union's Salyut program had multiple space stations that were operated intermittently depending on political and budgetary factors. Even the International Space Station, the most expensive single object humans have ever built, with a price tag over $150 billion, has uncertain long-term funding. There have been periodic debates about whether to continue operating it or retire it, whether the money spent on ISS could be better used elsewhere. A crewed Saturn mission would be far more expensive than ISS. It would cost several $100 billion, possibly over $1 trillion, depending on the mission architecture and how costs are accounted. Maintaining political and public support for such an expensive mission for 14+ years, through multiple election cycles and changing national priorities, would be extraordinarily difficult. What if support collapses halfway through? What if the mission is deemed too expensive, or the results not worth the cost? Your crew is still out there, still committed, still depending on ground support and expecting to be recovered when they return. But the will to support them might not be there. This is a risk that's hard to quantify, but very real. There's also the technical challenge of Earth return itself. Coming back to Earth from Saturn is different than coming back from the Moon, or even from Mars. The speeds involved are much higher. When you return from Saturn, you're falling inward toward the Sun. The Sun's gravity accelerates you as you travel. By the time you reach Earth's orbit, you're moving very fast. Much faster than a spacecraft returning from the Moon. Apollo spacecraft returned from the Moon at about 25,000 miles per hour relative to Earth. That's fast. And it required a carefully designed heat shield to protect the crew during re-entry. A spacecraft returning from Saturn would be approaching Earth at even higher velocities. The exact speed depends on your trajectory and how much propellant you use for deceleration, but you could easily be approaching at 30 to 40,000 miles per hour or more relative to Earth. Shedding all that velocity requires either enormous amounts of propellant for powered braking, firing your engines to slow down, or a very precise aero-capture maneuver where you dip into Earth's atmosphere at exactly the right angle to slow down through atmospheric friction. Aero-capture is more propellant efficient than powered braking, but it's extremely risky. The margin for error is tiny. If your approach angle is too shallow, you skip off the atmosphere like a stone skipping across water. You don't slow down enough and bounce back into space. If you don't have enough propellant to circularize your orbit, you might end up in a highly elliptical orbit that takes you far from Earth again, or worse, escape Earth entirely and end up in a solar orbit. Either way, you're not landing, and you might not be able to recover. If your approach angle is too steep, you enter the atmosphere too fast and experience G-forces that could kill the crew or cause the spacecraft to break apart. The heat generated by atmospheric friction would be immense. The spacecraft could burn up before slowing down enough for safe landing. The entry corridor, the range of acceptable entry angles, is very narrow. For Apollo returning from the Moon, the entry corridor was about half a degree wide. Enter half a degree too steep, and you burn up. Half a degree too shallow, and you skip off. That's how precise you have to be. For a high-speed return from Saturn, the entry corridor might be even narrower. And you're performing this maneuver after 14 years in space. Your navigation systems have been operating for 14 years, accumulating errors, possibly degraded by radiation damage. Your guidance computers might be glitchy. Your sensors might be less accurate than they were at launch. The crew is fatigued, possibly dealing with health issues, their cognitive function potentially affected by years of radiation exposure. Communication with Earth has multi-hour delays, so you can't get real-time guidance from ground control. You have to execute the aero-capture maneuver based on pre-planned parameters and autonomous navigation. Everything has to work perfectly. One mistake, one sensor giving a bad reading, one calculation error, and you die within sight of home after surviving everything else. The cruel irony of dying on the doorstep after making it back from Saturn would be devastating. Even if you successfully perform the aero-capture and enter Earth orbit, you're not done. You still need to deorbit and land, probably in a capsule similar to Apollo or Orion or Soyuz. This requires another set of maneuvers. You need to lower your orbit until your trajectory intersects the atmosphere at the right location for your landing site. You need to orient the spacecraft correctly so the heat shield faces forward. You need to execute the deorbit burn at precisely the right time. And then you endure re-entry, which is violent. The spacecraft slams into the atmosphere at thousands of miles per hour. The air compresses in front of the heat shield, heating to thousands of degrees. The heat shield ablates, burning away to carry heat away from the spacecraft. The crew experiences several Gs of deceleration, being pressed back into their seats with several times their normal weight. Apollo astronauts experienced peak deceleration of about 6.8 Gs during re-entry. They described it as intense but manageable for healthy astronauts who'd only been in space for a week or two. Your Saturn crew, after years in space, will struggle with even 1 G of acceleration. Their bones are weaker. Their muscles are atrophied. Their cardiovascular systems are deconditioned. Subjecting them to 4 or 5 or 6 Gs of deceleration is dangerous. It could cause bone fractures, particularly in vertebrae or ribs. It could cause the heart to struggle to pump blood against the increased effective weight. It could cause loss of consciousness if the brain doesn't receive enough blood. Medical teams would need to be prepared for crew members who can't walk unassisted after landing. Apollo astronauts, after missions lasting only days, sometimes needed help getting out of the capsule after splashdown. They were weak and unsteady after experiencing re-entry, deceleration, and then suddenly being back in full Earth gravity. Your Saturn crew would be in much worse condition. They might not be able to stand at all for days or weeks. They'd need extensive medical care immediately after landing. Some effects of their 14-year journey might be permanent. Bone density loss in long-duration spaceflight is partially reversible, but not completely. Astronauts who spend a year on ISS eventually regain most of their bone density, but not all. There's some permanent loss. For a 14-year mission, the bone loss would be much more severe. Even with the best rehabilitation, your crew might face lifelong increased fracture risk, osteoporosis developing earlier than it would have otherwise, skeletal problems that affect quality of life. Radiation exposure increases cancer risk for the rest of their lives. They'd need ongoing medical monitoring to catch cancers early. The psychological effects might linger. Readjusting to life on Earth after 14 years in space would be difficult. Earth would feel crowded, noisy, overwhelming. The open sky might feel uncomfortable after years of living in confined spaces. Some crew members might struggle with the transition. They might miss the clarity of purpose they had during the mission. The intense camaraderie of a small crew working together for survival. The sense of doing something important and unprecedented. Returning to ordinary life might feel anticlimactic or empty by comparison. This is something that Antarctic researchers and submariners sometimes report after long deployments. The intensity of the isolated experience creates bonds and feelings that are hard to replicate in ordinary life. You're asking people to sacrifice 14 or more years of their lives, their health, and possibly their future well-being for this mission. That's an enormous sacrifice. The question becomes, is it worth it? What scientific knowledge or other benefits justify asking humans to take these risks and make these sacrifices? Robotic missions can accomplish most of the science at a fraction of the cost and risk. Cassini operated at Saturn for 13 years. It discovered new moons and moonlets embedded in the rings. It mapped the ring structure in unprecedented detail, revealing intricate patterns and dynamics. It studied Titan's atmosphere and surface, mapping lakes and seas of liquid methane, finding evidence of a hydrological cycle and complex organic chemistry. It found evidence of subsurface oceans on Enceladus and possibly other moons. It studied Saturn's magnetic field, atmosphere, and interior structure. It observed seasonal changes in the Saturnian system over nearly half a Saturn year. It returned data that revolutionized our understanding of Saturn, its rings, and its moons. And it did all this without risking human lives, without the massive life support infrastructure required for humans, without the need to return. The mission cost roughly $3.26 billion over its entire lifetime, from development through launch, mission operations, and data analysis. That's expensive, but not compared to what a crewed mission would cost. A crewed mission to Saturn would likely cost several $100 billion to over $1 trillion, depending on the mission architecture, how many launches are required, whether you're using existing technology or developing new propulsion and life support systems, whether you're planning one mission or developing infrastructure for multiple missions. For the same money, you could send dozens of robotic missions to Saturn and every other interesting destination in the solar system. You could build enormous ground-based telescopes. You could launch space-based observatories studying every wavelength of light, from radio to gamma rays. You could fund extensive research programs studying planetary science, astrobiology, cosmology. You could advance human knowledge far more with many robotic missions than with a single crewed mission to Saturn. The scientific return on investment for a crewed Saturn mission is questionable at best. So why send humans at all? The main argument is that humans are more adaptable than robots, better at making decisions in unpredictable situations, capable of performing complex repairs and adaptations that robots can't, able to recognize the unexpected and pursue it. This is true on Earth and in situations where humans can interact directly with their environment. But at Saturn, humans would be encased in spacesuits, limited in what they can touch and do, dependent on life support systems, operating under severe time and resource constraints. Many of the advantages humans have on Earth don't fully apply. A well-designed robot with good AI might actually be more effective for many tasks. Robots don't need life support. They don't accumulate radiation damage to biological tissues that will cause cancer. They don't need food or water or sleep. They don't suffer psychological stress from isolation. They can be designed to work in extreme cold without complicated heating systems. And robotic capabilities are improving rapidly. The robots we'll be able to send to Saturn 20 or 30 years from now will be far more capable than today's robots. Advances in artificial intelligence, machine learning, computer vision, and autonomous systems are happening fast. Future robots might approach human levels of adaptability and decision-making in many tasks, without requiring the enormous life support infrastructure that humans need. The case for sending humans to Saturn gets weaker as robotic capabilities improve. Unless there's something fundamentally irreplaceable about human presence, something robots can never do, no matter how capable they become. It's hard to justify the cost and risk of crewed missions to the outer solar system. There's also the question of planetary protection and contamination. Saturn's moons, particularly Enceladus and Titan, are high-priority targets in the search for life beyond Earth. Enceladus has a subsurface ocean in contact with a rocky core. There's evidence of hydrothermal activity, chemical energy sources, and organic molecules detected in the plumes erupting from the South Pole. All the ingredients needed for life as we know it are present. If life exists anywhere in the solar system beyond Earth, Enceladus is one of the top candidates. Titan has complex organic chemistry, liquid environments, and energy sources. The conditions are different from Earth, too cold for liquid water, but life might find a way if it can use liquid methane or ethane as a solvent instead of water. It's possible that life exists on one or both of these moons. Different from Earth life, adapted to different conditions, but life nonetheless. If we send humans to these moons, we risk contaminating them with Earth microbes. Despite our best sterilization efforts, it's nearly impossible to completely eliminate microbial contamination on a crewed spacecraft. Humans shed bacteria and fungi constantly, from skin, from breathing, from every bodily function. Our bodies are ecosystems containing trillions of microorganisms, hundreds of species living on and in us. Some of these organisms are extremophiles, capable of surviving in harsh conditions that would kill most life. They can tolerate radiation, extreme cold, desiccation, high salinity, extreme pH levels. If even a few Earth microbes reach Enceladus's ocean or Titan's surface and manage to survive, they could contaminate a pristine alien environment. We've potentially destroyed the very thing we came to study. And we've made it nearly impossible to determine whether any life we subsequently find is truly native or was brought from Earth. This is called forward contamination, and it's a serious ethical and scientific concern. International planetary protection protocols exist to minimize this risk. Spacecraft sent to potentially habitable worlds are carefully sterilized. They're assembled in clean rooms. Components are baked at high temperatures or exposed to radiation to kill microbes. Strict protocols are followed throughout assembly and testing. Even with all this, complete sterilization is difficult. Some microbes always survive. For robotic missions, the risk can be managed to acceptable levels. But crewed missions present a contamination risk that's orders of magnitude higher. Humans produce microbes constantly. You can design airlocks and contamination control procedures, but the risk of accidental contamination is much higher when humans are directly involved. Some scientists and ethicists argue that we shouldn't send humans to potentially habitable worlds until we've thoroughly explored them with robots first. We should search for native life. We should characterize the environment. We should understand what's there before we risk contaminating it with Earth life. Only after we've confirmed the presence or absence of life should we consider sending humans. By that time, we might have decided that robotic exploration is sufficient and that human missions aren't necessary. This could delay crewed missions to Saturn's moons by decades or even indefinitely. The timeline for a crewed Saturn mission keeps getting pushed further into the future, the more carefully you examine the challenges. We don't currently have the technology for long-duration life support systems that can recycle air and water with near-perfect efficiency for 14+ years. ISS systems require regular resupply of consumables and spare parts. We don't have propulsion systems that make the journey practical. Chemical rockets work, but require enormous mass in low Earth orbit. Nuclear, electric, or ion propulsion could reduce propellant requirements, but would take just as long or longer. More advanced concepts like fusion propulsion or antimatter drives are purely theoretical. We don't have effective radiation shielding for multi-year deep space missions. We have concepts, water shields, hydrogen-rich materials, magnetic deflection systems, but nothing has been demonstrated at the scale needed. We don't have medical countermeasures for the physiological effects of multi-year microgravity exposure. We don't have artificial gravity systems unless you count rotating spacecraft designs that have never been built. We're working on these technologies. Research is ongoing. Progress is being made. But it's slow and expensive, and many of these technologies are decades away from operational readiness. The Artemis program aims to return humans to the Moon in the 2020s. That's a necessary stepping stone, relearning how to operate beyond low Earth orbit, demonstrating technologies that will be needed for Mars and beyond. From there, crewed missions to Mars are probably decades away. Optimistic timelines suggest the 2040s or 2050s. More conservative estimates push it to the second half of the century. Saturn is far beyond Mars in difficulty. Everything that's hard about Mars is harder for Saturn. Longer journey, more radiation, worse communication delays, more extreme isolation, much more demanding propulsion requirements. Realistically, A crewed mission to Saturn is probably 50 to 100 years away at minimum if we pursue it. Maybe longer if we decide that robotic exploration is more effective and don't prioritize crewed missions to the outer solar system. Maybe never if we conclude the risks and costs outweigh the benefits. The people alive today who dream of traveling to Saturn will almost certainly never see it happen. Even children today might not live to see it. This is a multi-generational challenge. And that brings us to the deeper question. Should we send humans to Saturn? Is it something we ought to do? Even if we eventually can. There's an argument that exploration is intrinsic to human nature. We've always pushed boundaries, climbed mountains because they were there, crossed oceans to see what was on the other side, ventured into deserts, jungles, polar regions, the deepest ocean trenches. We explore because curiosity and the desire to see new things, to go where no one has gone before, are fundamental parts of who we are. By this argument, we should send humans to Saturn for the same reason we sent them to the moon. Because it's there. Because we can, or will be able to eventually. Because the challenge itself is worthwhile. Because doing difficult things, achieving what seems impossible, is how we grow as a species. There's nobility in this view. The Apollo program inspired generations. It advanced technology, pushing the boundaries of what was possible in computing, materials, science, life support, propulsion. It demonstrated what humanity can achieve when we commit to a great goal. It gave people hope and pride, and a sense that the future could be better. A crewed mission to Saturn could do the same on an even grander scale. It would be the most difficult journey humans have ever attempted. The people who go would be heroes. Their names would be remembered for centuries. The mission would inspire a new generation of scientists, engineers, explorers. It would drive technological advancement in areas that would benefit life on Earth. The technologies developed for long-duration, deep space life support could help develop sustainable systems on Earth. Advanced propulsion could revolutionize satellite deployment and space resource utilization. Medical countermeasures for radiation and microgravity could have applications in healthcare on Earth. And the knowledge gained, the scientific discoveries about Saturn, its rings, its moons, possibly even finding evidence of life beyond Earth, would be invaluable. It would change our understanding of the universe and our place in it. But there's a counter-argument. Exploration should be pursued responsibly. We should weigh costs against benefits, risks against rewards. We should use our limited resources wisely, prioritizing missions that return the greatest scientific value per dollar spent and per human life risked. We should send robots where robots are effective and save human missions for situations where humans are truly necessary. By this argument, sending humans to Saturn might be possible someday, but it's not the best use of our limited resources. We could accomplish more science, more exploration, more benefit to humanity by investing in multiple robotic missions, advanced telescopes, and research programs. Rather than spending $1 trillion on one crewed Saturn mission, we could send 20 robotic missions to Saturn, Mars, Venus, Jupiter's moons, Neptune, asteroids, comets, and every other interesting destination. We could build massive ground-based telescopes that would revolutionize our understanding of exoplanets and distant galaxies. We could fund astrobiology, research, laboratory experiments, studying the origins of life, searches for biosignatures on other worlds. The total scientific return might be far greater than what one crewed mission could achieve. Both views have merit. The tension between them reflects deeper questions about what we value as a civilization, what we're willing to risk, what kind of future we want to build. There's no single, objectively correct answer. Different people, different cultures, different time periods will reach different conclusions. What seems impossible or foolish today might seem obvious and necessary to our descendants. What seems like a worthwhile challenge to some might seem like wasteful risk-taking to others. The conversation itself is valuable because it forces us to think carefully about why we explore space and what we hope to achieve. Are we exploring for scientific knowledge, for resources, for the survival of our species if something happens to Earth, for the inspiration and technological advancement, for the simple human desire to see new horizons? All of these are valid motivations, and they lead to different conclusions about which missions to prioritize. One thing is certain. If we do send humans to Saturn someday, it will be one of the most difficult and dangerous undertakings in human history. More difficult than the Apollo moon landings. More dangerous than Antarctic expeditions or deep-sea exploration. It will push human endurance, ingenuity, and courage to their absolute limits. The people who go will know the risks. They'll know that the mission might fail, that critical systems might break down, that they might not make it back, and they'll go anyway. Why would anyone accept that risk? Maybe for the same reason people climbed Everest when it was almost certain death, or sailed into unknown oceans when maps ended at the horizon and sea monsters were considered real possibilities, or volunteered for the first space flights when rockets exploded more often than they succeeded. Because some people are driven to push boundaries, to see what's beyond the next horizon, to test themselves against the ultimate challenges. Because the prospect of being the first human to stand on Titan's methane-soaked surface, to see Saturn's rings edge on from orbit, to collect samples from Enceladus's geysers, to witness sights no human has ever seen, is worth almost any risk to them. Because they believe the knowledge gained, the inspiration provided to future generations, the technological advancement driven by overcoming these challenges, justifies the sacrifice. These are the people who will go to Saturn if we ever send them. Not because the journey is easy, not because success is guaranteed, but because it's the hardest thing humanity has ever attempted, because it represents the ultimate test of what we can endure and achieve. And they'll know, going in, that coming back is far from certain, that Saturn might become their final resting place, that the ringed giant might be beautiful, might be scientifically fascinating, might offer views that would take your breath away, but it's also a trap in some ways. A gravity well in the outer solar system that's relatively easy to fall into and extraordinarily difficult to escape from. The physics are unforgiving. The distances are immense. The challenges multiply at every stage of the mission. Getting there is hard. Surviving there is harder. Operating in that hostile environment for the months or years needed to accomplish mission objectives and prepare for departure tests, human capabilities at every level. And coming back might be hardest of all. Coming back requires that everything works perfectly for 7 more years after years of operation have already stressed and degraded systems. It requires that the crew remains functional, despite accumulated radiation exposure, bone loss, muscle atrophy, and psychological strain. It requires that political and public support holds for 14+ years, so that ground support infrastructure remains in place. It requires that nothing critical fails during the return journey. It requires executing a high-precision Earth return maneuver after 14 years in space with degraded equipment and a fatigued crew. Any one of these could fail. And if any one fails, the mission fails. People don't come home. And that's why anyone who goes to Saturn might never come back. Not because we're planning one-way missions, though that's been suggested. Not because the mission will necessarily fail, though the risk is high. Not because the technology is impossible, though much of it doesn't exist yet. But because the combination of challenges, the cumulative effect of all the difficulties we've discussed, creates a situation where return is uncertain, where even with perfect planning, perfect execution, and considerable luck, things could still go wrong. Because space is unforgiving. Because Saturn is nearly 1 billion miles away. Because the universe doesn't care about human ambition or courage or determination. The laws of physics are absolute. They don't make exceptions for human dreams. Saturn will still be there, beautiful and mysterious, whether we visit or not. The rings will still sparkle in the sunlight. The moons will still orbit. The science will still be there to discover. We can explore from a distance through telescopes and robots. We can learn without risking human lives. We can understand without going there ourselves. Or we can accept the challenge, develop the technology over decades, train the people, build the spacecraft, launch the mission, send our best and bravest to see for themselves what Saturn is really like. Both paths teach us something about who we are. Both have value. The choice isn't obvious. And maybe that's okay. Maybe it's a conversation we'll keep having for generations. Maybe our grandchildren will still be debating whether to send humans to Saturn, or maybe they'll have moved past it to wondering whether we should send humans to Uranus or Neptune, or even interstellar space. But understanding why Saturn is so difficult, why return might be impossible, why the challenges are so severe, helps us appreciate the magnitude of what we're considering. It's not a matter of just building a bigger rocket. It's a fundamental challenge that tests the limits of current human capabilities and technology. And whether we ever send humans there or not, Saturn will remain. A testament to the vastness of the solar system. A reminder that there are places in our cosmic neighborhood that are almost impossibly difficult to reach. Places where humans might be able to go, but might not be able to return from. That's the reality of deep space exploration. That's the price of pushing into the outer solar system. And that's why Saturn, beautiful as it is, remains a dream on the distant horizon. A challenge that might take centuries to accept. A journey that might never be worth the cost. But one that captures the imagination, nevertheless. Because Saturn is there. Because the universe is vast and full of wonders. And because some part of us will always wonder what it would be like to go there. Even if the journey is dangerous. Even if return is uncertain. Even if the price is higher than we can pay. That's who we are as a species. Curious, ambitious, sometimes foolish, always dreaming of the next horizon. And someday, maybe, those dreams will take us to Saturn. But anyone who goes should know the truth. The journey there is long and dangerous. The destination is hostile. and the path home is anything but guaranteed. Physics doesn't negotiate. Distance doesn't care. And Saturn, for all its beauty, might hold anyone who visits in its gravitational embrace forever.